Okay, little over 6 o'clock, 6:01. Let's get started. There total 35 participant, 37. You can start. So we were supposed to start deeper detail into the MIPS assembly language, and next 2 days we will be spending on understanding these MIPS assembly language constructs and different functions, basically review of your textbook appendix section, uh, which is like these. Let me share that with you. Yeah, this one. Right, and today we'll be concentrating on mostly on the addressing modes and etc. And then there are these, we'll review uh, all these directives, especially the one we'll be using most in the class is you'll see .ascii, ASCII, .byte, .data, extern sometime, double float, global, global, etc. So basically, you need to review these pages and all the instructions. You need to get familiar with yourself from this topic. And next day, we'll be moving into more like an conditional branching and jumping, looping, etc. And after that, we'll discuss about the procedure implementation or function implementation in the assembly level. So with these three lectures, I hope you'll be gaining much insight into the MIPS assembly as a language. Any question from anyone?
I had a question about add you.
Okay.
So I suppose like in the green sheet, it says that it's add unsigned, but then I suppose here it's add without overflow.
Oh, come again? Yeah, it's a green sheet. It says the add unsigned, yes, and
So in the lecture 10, you explained that add you, like it says over here, it's addition without overflow.
yeah, it's how should I say? This addition ADU, it's kind of equivalent to saying that in terms that okay, what this specific one is mentioning is that this instruction does not create an overflow signal in the program. So that means if you are adding two huge numbers, huge values, unsigned value, and that value can no longer like represented within 32-bit, you will get some answer, but you won't have an overflow exception from that instruction. That's what it is without overflow is saying. So it's basically as equivalent as you are doing an unsigned addition.
But in the case where like you add, if you like add two numbers in two's complement and like there was an overflow and one of them was negative, wouldn't that be subtraction, or is that equivalent to just doing addition anyway?
So that's anyway, it's an addition anyway. So remember this add, subtract, these are all like for our reference, right? And we think in terms of values and its signs like negative number, positive number, or I should say negative values, positive values. But at the computer and processor level, it's all comes down to the logical operation between the bit values. So it's all logical operation. There is nothing mathematical about it. So that means we are basically having two operands with like two bit patterns, and we are manipulating these bit patterns to come up with a result bit pattern. So logically manipulating the bits and come up with a result bit pattern. Now, how would we treat that result bit pattern? Whether we treat them as a signed value or unsigned value or floating point number, double number, it really depends on the consumer of that information and make a decision how it wants to treat that series of bits, right? So at the logical level, at the computer processor level, there is no distinction often like signed value, unsigned value doesn't matter. It's all comes down to a bit pattern manipulation. This will be much clearer with the second half of our study, like after the midterm, when we start looking into these specific integer operations, that how the addition is done or multiplication is done or subtraction is done. Probably this concept will become more clear during that time. Okay, so hold on to that point. But so far, just think these are bit manipulation function resulting in a value bit pattern which gives us a value for addition of two bit patterns, like two values, something like that. Make sense?
Okay, yeah.
Yeah, so hold on to the second half of our discussion after the midterm when you start looking into this logical operation. What is the logical operation behind this arithmetic operation? And at that point, I hope it will become more clear to you guys. Okay, so any other question? Carter said, can you explain XOR? XOR as in this function, I assume you're asking about this XOR operation here. Right, okay. Let me find out. Yeah, exclusive OR. So XOR is a XOR logic operation. Do you guys know what the XOR logic operation is?
Yeah.
Exclusive OR, exactly. So what it does, it basically, so RS and RT, those are two 32-bit pattern. So it basically bitwise XOR. So it XOR between bit 0 of both operands, and that's become the result. And then bit 1 of the both operands, that become the result, and so on and so forth. So basically, it's a bitwise XOR operation between these two 32-bit patterns. Carter, it makes sense or? Okay, in chat, Carter said it's fine. All right, then basically, where do we start? Okay, most important from this page is this part, addressing mode. You need to understand very carefully what these addressing modes are and how they're used to. That's one thing. And another thing in this concept, in this topic, I want to show you the green sheet once again with you. I believe I have shown you already in previously, like this is the 2-page document which compacts many information, and you need to really learn yourself how to read this, okay, how to extract information out of that. For example, it has a list of like many commonly used instruction sets, and it explains their format and what their functionality is, and then it actually gives opcode and function code for that specific instructions. And also it has some footnotes along with that, like if you say that, okay, number one, it footnotes associated with the add, and that, yes, that may cause overflow exception. And then let's see, if you look at the, okay, something like RS plus sign extension immediate, you can go there in the legend section and really see what this sign extension means, right? It's take the immediate bit pattern and then take the MSB of that 16 bit and repeat it for 16 times. That's the sign extension immediate. It also talks about the zero extension immediate, what that means and wherever that is. Uh, Interesting part is this branch address. What is the branch address really is? What is the jump address really is? So you need to explore these a lot and know how to read them. It also describes your instruction format. Towards the end of the semester, we'll come to this floating point instruction. Then it has list of registers, their usage model, though obviously our argument register convention is different than this table, but let's keep that in mind. It has, along with this, all the like a long set of ASCII codes, like for different letters and symbols and so on and so forth. It has a format for the fraction IEEE 754, which we'll be discussing towards the end of the semester. It has this MIPS memory allocation suggestion or model, MIPS model, that part, so you know what is the power up address, what is the global pointer power up address, so on and so forth. So those are the things. It talks about the data alignment. It's a nice, like a flashcard to you to remember those data alignment things. And it also has a unit conversion table, basically. This is an like one stop place to get many useful information that you will be needed to do any problem or any other like during the exam and so on and so forth. Please make sure you know how to read these 2 pages. All right, questions so far? Okay, now let's come to some discussion topics. Okay, 6:15. All right. So before we start with the problem in hand, I like to explain, like when you basically learn some new language, like what are the things you should actually go and look after to learn. So let me explain that a bit. Like any language, it doesn't matter whether you are learning an assembly language or learning a high-level language like Java, C, C++, or a scripting language like Python or Perl or Tcl, whatever it is. So basically, there are like steps, like number one, data layout. That basically, in terms of high-level language, what it means is basically data definition. How do you define data? Like in the high-level language, you probably declare the data as an integer type or character type, string type. In Python or scripting, you don't need to declare a type upfront. Like in a low-level language like this assembly, what we are dealing with so far is basically defining a .data section and laying down initial constant values or variables in terms of labels and putting that on those values onto the memory, storing them onto the memory. In fact, the high-level language, when you compile it and assemble it, compiler does it for you. It creates a data section for you. if it is a global data section as a high level concept, or at least it creates the these local variables in the frame and all this stuff. So when we deal with the function implementation, we'll look into that part. But ultimately, it is you need to look for how do you want to lay down your data, lay out your data into the memory through the declaration to the definition, whatever, whatnot. And then number two is the data manipulation. What are the available functionality you have for the manipulating like two variables or two set of values? Starting from the very basic operation like addition, subtraction, etc., to like maybe as complex as like all these trigonometric operation like sine, cos, etc., or maybe more complex operation through the mathematics library like Fourier transformation and so on and so forth, where it's more about how do I manipulate data? How do I manipulate data? So you need to look for those specific instruction for those part. Next important thing is basically decision making. It is in the high level language, it is more like an if then else, right? If then else kind of thing. So any language you try to learn, you basically need to know how do you make decision in the program. How do you make how do you write a decision code in the program, just in conceptual if then else. Okay, whether it is Python, Java, C++, doesn't matter. You need to go and find out decision making mechanism. And then next is the looping, like for loop, while loop. Like high level language actually gives you lot many flavors: for, while, repeat until, etc., etc. Those kind of things you need to look for any language. How can you implement a loop inside a program? Okay, whether it is assembly, Python, Java, doesn't matter. You need to look for that abstract concept. How do you loop? And next is how do you make reusable code in general? Reusable code, aka most common to the functions or procedures. Some language call it procedure. Some language differentiate them. Some language don't differentiate the function, procedures, and so forth. But it's more like in making a reusable code. So function and procedure concept is more like you're writing down on a series of like sequence of code for a common goal. Like maybe it's like an factorial computation. Maybe it's an other complex things you want to achieve through that set of code, and you will be reusing it in your main application program like many places. So instead of rewriting the code many times, you are basically abstracting and encapsulating into an reusable code module and how you are going to use them. So basically you need to look for those kind of feature in any language you want to learn. So in this MIPS language, we will be learning, we were somewhat learning about the data layout and definition so far. In this today's topic is more about data manipulations and somewhat data layout. And then next day's topics is more like in decision making and looping. And then we have whole one day topic for making reusable code, or at least we'll concentrate on the function and procedure. There are other ways like using the macros and other stuff. That is also reusable code. We're not talking about that. Assembly level macro, we have already done it. We'll not be talking about that one. We'll be specifically looking for this function procedure implementation at the MIPS level. Question?
Professor, can data structures be implemented in MIPS as well?
Data structure?
Yeah, like you know how we have libraries for like maybe let's get say selection sort or like those kind of operations.
Mm-hmm.
So can we do that like in MIPS as well? When we talk about reusable code, is that the code we're talking about?
In a sense, yes. In a sense, yes. Uh, so if your question is more like, can we build a library of MIPS functions, procedure, reusable code? Yes, we can. Is it available? Answer is no.
Oh, it's not available.
No, it is not.
Okay, alright. So like we don't have like libraries in MIPS like we do have in higher language.
Absolutely not. And that's not the target for this class. Remember, we are bare
Yeah.
minimum. We are going in a bare minimum mode.
Okay, we're
With
just learning about how the hardware functions rather than like
exactly,
writing the actual code for problem solving in real world.
exactly,
Yeah.
right? So
Okay.
no one like needs those libraries, and no one directly program in assembly language in most of the time. I'm not saying
Like
it is not absolutely needed, but it's through the high level interface even then, like not.
like
Yeah.
back in the day when like the other programming languages were not that common, like
Yes, back in the
those
days it
libraries.
used to
Okay.
available. Yes,
Okay. So,
back
thank you.
in the days it's available. And also in theoretical sense, if when you are linking with a library in an application program which has this reusable code, like all these, for example, in C++ world, we have the STL library or standard template libraries, which has provided all the data structure like a stack or queue or a hash table, etc. Right? What are they? They are not a high level program anymore. They are basically either a templatized code or it's a compiled library with an object code. So it is already in essence already translated into the assembly level and machine level code. Uh, and a previous, like whoever is providing the library to.
Okay. I see.
All right. So let's do one thing, okay? So look at this set of instruction. Like I have 1, 2, 3, 4, 5, 2, 4, 5, 5 instruction. Okay, spend yourself 5 minutes to think what are the addressing mode involved in this list. Okay, addressing modes involved in this list. Let me just what are the addressing modes? Okay, we have these 6 instructions. Just think 5 minutes, 6:30. We'll be back. Maybe in the 6:30, what I'll do, I will basically open up the breakout session for you for another 10 minutes to discuss this problem within your group. So first think yourself very critically, what are the addressing modes involved with these set of instructions? Okay, I am now opening all the breakout room for you to discuss about 10 minutes among yourself, and cross-check your answers, whatever things you need to discuss for this specific problem. I think times is up, and let all of you guys come back to the session. I think all of you are back now. Who wants to go? Which group?
I don't mind going with my group.
Okay, Russell. Yeah, sure.
Sorry, Josh.
Oh, Joshua.
That's okay. That's okay.
Russell's face came up on the Zoom. So.
Oh, okay.
Okay. Yeah.
So for add, we thought that add would be the register addressing,
Okay. Why?
since it only takes registries as its arguments.
Okay. Okay. And this is itself is a art type instruction, right?
Yes, R type.
Mm-hmm. So how about the next one?
The next one was, we figured it was the immediate addressing,
Okay.
because it uses an immediate for its third argument,
Okay.
which would mean it's, yeah, type of I.
Mm-hmm.
And then load word was displacement addressing.
Okay.
And then JAL was pseudo direct addressing, which
Okay.
is the jump command.
Mm-hmm.
And then B&E was the PC relative addressing, since it's using a text value.
Okay. So anyone else wants to add on top of that?
Would it be accurate to describe an instruction using multiple addressing modes?
Sure.
I guess because like with add I, there's both a register and immediate value. So would that be both register and immediate?
Why do you think so? So you are saying that, okay, this is like both register and immediate. Why?
Oh, and immediate? Would that, I guess, be accurate?
Okay, so that's your combination, like you are thinking that it is add I is both register and immediate.
Yeah.
Okay, so can you reason? Can you tell us a reason?
Because the assembler would have to like get both the address of the register
Mm-hmm.
and use that immediate value. So
Okay, okay. So how about the load word, the next one?
both register and the displacement addressing.
Okay. How about the next one? Is that any other?
Just pseudo addressing.
Okay, and how about this B&E?
Both register and pseudo addressing, I think.
Okay, so this table looks good to you, Charlotte?
Except I guess for our group, we said for the last one, it was pseudo addressing instead of PC relative.
Oh, so you think this is this one should be pseudo addressing instead of PC relative?
I guess like on second thought, PC relative makes a lot of sense.
Okay, all right. So what I say is, okay, this is correct because it is accessing the register. It is both reading the register T3 and the immediate field. So both the addressing mode is applied onto this instruction, and it's also writing back to the register. So this
Professor,
is also,
are you speaking right now? Because
yeah,
I can't hear anything.
Oh yeah,
Yeah.
Professor speaking right now.
I can hear him.
So yeah, maybe some intermittent problem. So basically what I'm saying is this, the second one, the first one is no problem because first one is all about register addressing because you see that all our, like this register is read and also T2, this is being read and then sum up and then stored back onto the register. So that's all about register. Now add I, it's a type of instruction, is I, but while it is operating, it's basically accessing one operand through the immediate access. So that's immediate addressing. And another operand through reading a register, that register mode. And it's also writing it back to the register. So that's a register mode. So this involves like both register and the immediate addressing mode. In essence, addressing modes is not directly connected to the type of the register. Like many of the students I have seen, they try to relate them. R is okay, it a register mode, I is immediate mode. Then in that case, why this I type becomes a base displacement, right? That's the reason. Basically, each instruction can be of like involve multiple addressing into it. So we need to analyze that very carefully. Load word, on the other hand, has what? It has immediate field access. That is immediate. So we didn't mark that. So we need to mark it. Okay, we need to mark it. So this is right. And then it actually has to read the S1, the base register. So that's this addressing. And base register content added with this offset 12 is basically gives you the memory address to be read. So now it is base displacement addressing, okay, during the memory access. And then of course, coming back to the stored value stored in the register, that becomes your register mode access. JL is more like pseudo accessing. There is no other thing to do. BNE is register plus PC relative. So register, because it need to read these two registers, it need to access those data, compare them. And if they are not equal, then it changes the program counter with relative to its current value, +4. Okay, so that's PC relative. And in fact, if you look at the data sheet, let me share that with you in a minute. Okay, this part. Where is my oops. This one. Look at the BNE here. BNE is more like if these two register content are not equal, then you do this PCs. This PC is the future value of the PC, like next program counter from where it needs to pick up the instruction with the current address of this current BNE instruction, whatever that address is, +4 plus a branch address. So this is kind of an offset with respect to the current value of the program counter +4. And this one, look at the branch address definition here. It is immediate and it appends to 0, 2-bit 0. And then 14-bit, it repeats the MSB of immediate 16-bit. So that's how it makes this whole 32-bit about the branch addressing that has to be offsetted. So its offset calculation is mostly like it picks up the immediate bit pattern, append 20 to it, and pick up the most significant bit of the immediate field and repeat it 14 times. So 16 plus 14 is 30 plus 2 bit of 0 gives you 32 bit address. Okay, so that's how why it is PC relative. It is relative to the program counter. It's relative to the program counter. Question so far?
So does it add another 4 because each instruction is like 4 bytes?
PC plus 4?
So like it's PC plus 4 plus the.
Yeah, you can think this way. Like each instruction, as you rightly said, each instruction contains is actually stored within 4 bytes. That means it's basically span within 4 address in the memory. So if my current address of the instruction is PC, that content of the program counter, then my next instruction's address is PC plus 4. This PC relative addressing is always computed with respect to the next instruction, not the current instruction. So that's why the PC plus 4 is there. So in a sense, hey, Charlotte, you have a question?
No, yeah, that makes sense.
Okay. Just to reiterate on that part, right? So basically, from this branch on equal and branch on not equal from our MIPS one pager, it says the PC equals PC plus 4 plus branch address, BA. Just I'm going for an abbreviation, BA, that is branch address. Now what
Professor, the MIPS green sheet is covering the Jamboard on Zoom.
Yeah, thank you. Thank you, Carter. So what I'm saying is the PC new is the PC current plus 4 plus branch address. So PC equal to PC plus 4 plus branch address may be a little bit confusing to you. Just to make sure that you have this clear conception is that this program counter is holding the address of the current instruction, which is like BNE, whatever BNE instruction it is executing now. It adds up 4 because this relative addressing is always respect to the next upcoming instruction. So that's why it adds up 4 on top of that. And then add an offset, okay, branch address. And what is that offset is? That offset is basically you take first LSB side, you add 2 zeros, then your immediate field, then you repeat the MSB's 16th MSB of the immediate field. You concatenate them, those bit amounts, and make the BA values. Okay. So in a sense, this immediate, like we all know the BNE I-type instruction format is this, like opcode, RS, RT, and immediate. So this is, in a sense, it is that offset in terms of number of instruction. So what this guy is encoding is that from this point, either go forward 10 instruction down, go forward, or go backward, let's say 5 instruction. So it is nothing about the addresses. Like, okay, go like 5 byte or 8 byte or 40 bytes, nothing like that. It's all encoding is that you need to go and go back either like 5 instruction or 7 instruction, or go forward 5 instruction, 7 instruction. Means like if this immediate value is -5 here, it really means go back 5 instruction. Okay, go back 5 instruction. Let me think if that makes sense. Yes, go back 5 instruction. And if it is really like something like +10, this value, this really means go forward 10 instruction. Okay, go forward 10 instructions. Now the question become like, go back and go forward. Is it respect to this PNE instruction or the next instruction? That is the question, right? Let me give a thought on that a little bit. Okay, you guys also think what needs to be done there. Let's say what I mean, let's say you have a code like, okay, instruction 1, L1, instruction 2, instruction 3, BNE to L1, instruction 4, something like that, right? So what do we put there? Is it like, let's say, if this condition makes, should I tell it to go back 1, 2, 3, like -3, or should I tell it go back to -4? Okay, so you guys need to think a little bit detail on this. I'll also think about this question and we'll converge onto our ideas. Question? All right. So this is one thing you need to think, okay? Tonight, tomorrow, then on Wednesday, we'll discuss what that would be. And with that context, I will give you one problem to think. Also, yeah, think in group, in your study group, okay? Think in your study group. This problem and the other problem I'm going to give you is basically, let's see if it comes right onto here. Okay, this is good enough. Let's say I have a piece of code. I have a piece of code, okay? I have a piece of code like this, and I wanted to compute the machine code for this guy and this guy. Okay, so this is your PC relative, and this is your pseudo direct. What are the machine codes for these two instructions? So first do it manually. First do it on paper with all the theories and that you understand with all the papers, and then cross check, then cross check in Mars. Okay, so don't go to the Mars right away. and see, okay, this is my address. Don't get to the answer. The important point is to how do you get that answer. That is the important point for you to understand. And that will possibly give you a deeper understanding of how this addressing mode affects your machine code generation. Okay, so as a group, please discuss that, like tonight, tomorrow, sometimes you set up and discuss this. First of all, this immediate field, what its content, is it relative to the next instruction, the jump back, so 1, 2, 3, 4, or with respect to the current instruction? And with that respect, I think you should do this exercise, that will possibly gives you answer back of this exercise. Question? Okay, so if we don't have any other question, I think we can stop tonight here a little bit early so that you have some time to think over. Okay, so just don't come to the answer right away. Just think over how do you approach those problems and study in groups. And we'll all see you on the Wednesday.
Okay, thank you, Professor.
Thank you.
Thank you.
Wednesday all.
Thank you, Professor. Sorry for interrupting you earlier.
Hey, no problem.